The construction of the Nisibi Bridge, spanning the Euphrates River in Turkey, was an impressive engineering achievement, involving a carefully sequenced series of technical and logistical operations. The project began in 2011 and concluded in 2015, overcoming complex environmental and structural challenges. Below is a detailed account of each construction phase, from foundation preparation to final cable tensioning. The first phase involved preparing robust foundations capable of supporting the bridge's 96-meter-tall pylons. This groundwork required the excavation of over 150,000 cubic meters of rock and limestone. Heavy-duty excavation equipment was deployed to clear the riverbed and create a stable base, ensuring that the pylons could securely anchor into the ground. The foundation work was especially crucial due to the location's proximity to the seismically active East Anatolian Fault. Engineers used C60 high-strength concrete, reinforced with 4,200 tons of steel rebar, specifically designed to withstand significant seismic shocks, thereby preparing the structure for long-term stability and safety. Once the foundation was secure, the next stage involved constructing the bridge's two main pylons. These towering structures were built incrementally, with engineers carefully pouring high-strength concrete layer by layer. The pylons were designed with internal reinforcement bars to absorb seismic forces. Their substantial height of 96 meters required extensive scaffolding and formwork. As the pylons rose, cranes lifted steel and concrete components to precise positions, and workers secured each section, ensuring that the entire structure would remain stable and well-aligned throughout construction. The pylons' robust design and composition allowed them to endure earthquake forces anticipated within a 2,475-year recurrence interval. Steel frames, critical to the bridge's central span and overall stability, were fabricated at a specialized facility in Osmaniye. These steel segments, each weighing up to 250 tons, were manufactured to exacting specifications, with precise angles, joints, and lengths to fit seamlessly upon assembly. Once fabricated, each segment was loaded onto large barges, which would navigate the Euphrates River to the bridge construction site. This method was chosen to facilitate transportation of the massive steel frames in the most efficient and secure manner possible. Once at the construction site, the next step was to hoist the steel frames and assemble them into bridge spans. Specialized heavy-duty cranes, positioned at either side of the bridge, lifted each frame segment from the barge to the correct height and position. Aligning each section was a painstaking process that required skilled coordination between crane operators, engineers, and ground crews. Once each segment was precisely positioned, workers welded the sections together to create a continuous steel deck. The welding process was intricate, requiring high precision to ensure seamless connections and prevent any structural weaknesses. Each weld was meticulously inspected to meet strict safety standards and provide the necessary load-bearing strength. After each segment was welded into place, the next step involved connecting the spans to the pylons. This phase required bolting and welding the steel frames to create stable, aligned sections across the length of the bridge. Engineers ensured that each segment fit precisely, adjusting and realigning as needed to achieve perfect connectivity. The frames were locked into position using a series of bolted plates and secured with high-strength fasteners. This interconnected framework would form the base for the bridge deck, ensuring stability and resilience. These cables, which provided essential support for the central span, ranged in length from 67 to 2,117 meters. The process involved anchoring one end of each cable to the deck and the other to the pylons. Specialized tensioning equipment was used to gradually tighten each cable to the correct level, balancing the load distribution across the bridge. Engineers monitored the tensioning process closely, adjusting each cable's position to ensure a stable and balanced load distribution, which was crucial for withstanding both traffic load and seismic forces. Throughout the cable tensioning, sensors installed along the bridge recorded real-time data on temperature, wind, and tension forces, allowing engineers to monitor any shifts or fluctuations that could affect alignment. The Nisibi Bridge project concluded successfully in 2015, establishing a critical transportation link between the Adıyaman and Diyarbakir regions. The bridge has since transformed regional travel, reducing dependency on ferry transport and fostering economic connectivity. Not only does it represent an engineering marvel, but it also exemplifies the capabilities of Turkish engineering expertise and resilience in overcoming complex logistical and environmental challenges. The Block Island offshore wind farm, located 3 miles off the coast of Rhode Island, represents a landmark achievement in the U.S. renewable energy sector as the nation's first offshore wind project. Developed by Deepwater Wind, this project is pivotal for the growth of the emerging American offshore wind industry and aims to provide clean, renewable energy to over 17,000 homes in Rhode Island. Its success has been due in large part to meticulous planning, precise engineering, and the collaboration of experienced maritime and wind energy companies, including Fred Olson Wind Carrier and Global Wind Service. The planning for Block Island took nearly 2 years, involving complex logistical coordination across multiple countries. The installation process began in Esbjerg, Denmark, where the project's installation vessel, Brave Tern, was loaded with 5 Haliade 150 to 6 MW turbine nacelles. Brave Tern is a specialized jack-up vessel with an 800-ton crane capacity and a payload of 7,600 tons. With such a heavy load, the team carefully planned and executed each placement to ensure safety and stability. Each component was slowly and precisely positioned to prevent the vessel from tilting more than 1 degree during the loading process. Brave Tern embarked on a 3,000 nautical mile journey across the Atlantic, stopping in Saint-Nazaire, France, to load turbine components weighing approximately 450 tons each. The vessel then continued its journey to Rhode Island, a voyage that required careful navigation and took 15 days. The experienced crew made use of the vessel's advanced propulsion system to navigate accurately and maintain stability under varying sea conditions. During the journey, experienced technicians from Global Wind Service joined the crew to help prepare for the offshore assembly of the turbines. Once the components arrived in Rhode Island, the Brave Tern team, along with offshore technicians, began the complex process of assembling the turbines. Installation involved coordinating with US-based barges, which introduced new logistical elements compared to the European offshore projects the crew was more accustomed to. The team handled everything from marine engineering planning to lift engineering and actual turbine installation, dealing with the added challenge of working far from immediate assistance and support. As a result, precision in planning and execution was crucial, especially for a project that required meticulous adjustments to accommodate different equipment and regulatory standards. The Block Island wind farm does more than provide renewable energy. It symbolizes the dawn of a new offshore industry in the United States. This project not only contributes to clean energy generation and reduced air pollution but also creates jobs and enhances technological expertise in the region. The success of this project underscores the potential of wind energy in the U.S., demonstrating the capabilities of offshore wind farms to contribute meaningfully to the nation's energy mix. The construction process of an onshore wind turbine foundation is a multi-step procedure that plays a crucial role in ensuring the safety, stability, and long-term operational efficiency of the turbine. This is especially true in regions with complex soil conditions, varying climates, or challenging weather patterns. Each step is carefully executed to meet engineering specifications and ensure that the structure can withstand environmental forces and loads over the turbine's lifespan. The construction process begins with excavation, where the area designated for the foundation is cleared of any vegetation or debris. Depending on the foundation type and the ground conditions, excavation depth and diameter can vary. For example, shallow foundations may only require the removal of topsoil, whereas deep foundations may necessitate the removal of several meters of soil to reach more stable layers. The excavation is conducted carefully to ensure it is level and aligned with the design specifications. Once the excavation is complete, the next critical phase involves placing steel reinforcement bars, rebar, within the excavated area. Steel reinforcement is essential for ensuring the foundation's tensile strength and the ability to distribute the weight and forces exerted on the wind turbine structure evenly. Rebar placement must be done according to the design specifications, with a precise grid pattern designed to enhance the concrete's load-bearing capacity. The rebar framework is carefully inspected for alignment and positioning to ensure structural integrity. Any deviations from the design, such as misaligned bars, can compromise the foundation's strength. The construction team typically uses lifting equipment to position and secure the rebar, ensuring that it remains in place throughout the concrete pouring process. Once the rebar framework is in place, the next stage is the pouring of concrete. The concrete mixture must be tailored to meet specific strength requirements, as dictated by the design. The composition of the concrete, including the proportions of cement, aggregates, and water, is critical to ensuring that it can withstand the loads it will be subjected to throughout the life of the turbine. The concrete is poured into the excavation carefully and evenly to ensure proper compaction and to eliminate voids. This step is essential because any air pockets within the concrete can weaken the foundation. After the concrete has cured and reached the necessary strength, final touches are applied to the foundation. These may include surface leveling and smoothing to ensure the surface is even and free of defects. Any minor adjustments are made to ensure the foundation meets the dimensional requirements outlined in the design. Precision is key during this phase, as even minor discrepancies can affect the alignment of the wind turbine tower, potentially leading to operational inefficiencies or structural issues down the line. Throughout this entire phase, quality assurance measures are implemented. This includes regular inspections to confirm that the construction process adheres to the design specifications and industry standards. With the foundation in place, preparations are made for the arrival of the turbine components. This phase involves constructing access roads and temporary facilities for workers and equipment. The wind turbine components, such as the tower sections, nacelle, and rotor blades, are transported to the site, often via oversized trucks and cranes, depending on the size and weight of the components. As the turbine components are delivered, they are carefully staged and positioned in preparation for the assembly process. Once all components are in place, the tower sections are assembled one by one, and the nacelle, which houses the turbine's critical mechanical components, is lifted into position atop the tower. Afterward, the rotor blades are attached to the nacelle, completing the turbine assembly. The first critical step in the wind turbine assembly process is the installation of the tower onto the foundation. The tower itself is the tallest structure of the wind turbine, and its stability is essential for the performance of the turbine. The foundation is typically a reinforced concrete base or a monopile, which is a large steel tube driven deep into the seabed or grounded in concrete, depending on whether the turbine is located offshore or onshore. Heavy-duty cranes, often referred to as crawler cranes or mobile cranes, are used for this critical phase of the installation. These cranes are capable of lifting extremely heavy and large components, such as the tower, which can weigh hundreds of tons. The tower sections are often pre-assembled on the ground in segments before being lifted into place by the crane. To lift the tower, the crane operator uses a precise system of ropes and pulleys, which allows the heavy section to be lifted vertically from the ground and positioned over the foundation. Once the tower is lifted into position, it is carefully aligned with the foundation, ensuring that it is vertical and secure. The sections are then bolted together or welded to form a single continuous structure, depending on the design of the wind turbine. Once the tower is installed, it becomes the central support for all other components, including the nacelle, rotor, and blades. The nacelle is the housing that contains the key components of the wind turbine's drive system, including the generator, gearbox, and electrical systems. The nacelle is typically mounted atop the tower and must be lifted into place once the tower structure is fully assembled. The nacelle is one of the heaviest parts of the wind turbine, often weighing between 60 and 100 tons. Heavy-duty cranes are again used to hoist the nacelle into position. It is carefully lifted from the ground or from a transport vessel, in the case of offshore wind farms, and positioned at the top of the tower. Once the nacelle reaches the top, it is carefully maneuvered into place, and the technicians use bolting systems or hydraulic systems to attach it securely to the top of the tower. Alignment is critical during this phase, as the nacelle must be perfectly positioned to ensure proper operation of the drive system. Once the nacelle is in place and secured, technicians proceed to connect the internal systems, which include electrical cables, cooling systems, and the drivetrain components. The drive system is responsible for converting the kinetic energy from the wind into electrical energy, making it a vital part of the turbine's overall function. The rotor of the wind turbine is composed of several parts, with the most important being the hub and the blades. The rotor is responsible for capturing the wind's kinetic energy and converting it into rotational energy. The rotor assembly is a key part of the turbine's performance and efficiency, and it must be installed with precision. Once the nacelle is installed and secured on top of the tower, the next step is to install the rotor hub. The hub is the central component of the rotor and serves as the connection point for the blades. The rotor hub is typically mounted on a large shaft that is connected to the gearbox inside the nacelle. The rotor hub must be positioned with care to ensure that it is properly aligned with the nacelle and the drive system. Once the hub is installed, the next step is to attach the blades to the hub. The blades are often stored on the ground before installation and are transported up the tower using cranes. The blades, which are typically made of lightweight composite materials, can range from 30 to 60 meters in length, depending on the size of the turbine. To attach the blades, cranes are used to lift each blade individually to the top of the tower. The blade is then bolted onto the rotor hub. This process is carefully coordinated to ensure that each blade is securely attached and properly aligned with the others. During installation, the blades may be adjusted to ensure that they rotate evenly and efficiently. The installation of the rotor and blades is a crucial step in the turbine assembly process, as the rotor is the component that directly interacts with the wind. Any misalignment or error during installation can cause significant performance issues or even damage the blades and hub. The assembly process of a wind turbine is a carefully orchestrated series of steps that requires precision, heavy machinery, and skilled labor to ensure each component is installed safely and effectively. The process involves multiple stages, starting with the lifting and securing of the tower onto the foundation, followed by the installation of the nacelle, rotor, and blades. This highly specialized work requires the use of large cranes and meticulous planning to ensure the turbine operates efficiently for decades.